Okay, now I'm also recording. Sorry for forgetting everything I have to do. So let's go back to this and hopefully everything will work fine. What is a predictor function, a prediction function? Well, it's a function of past information. We may just call it, I don't know. Well, we'll just call it X. It doesn't really matter if we provide a T underneath. Of course, in forecasting, X will contain past information. But this is more general, a general reasoning we can do. This applies also to cross-sectional data prediction. Okay, whatever prediction you do using either machine learning or statistical models. So, the prediction will be a function of known information. And how do we decide the shape of this function based on the data? Of course, we have a sample of both the variable we have to predict and the variables we want to use to predict. And so we want in some way to, well, we can compute whatever the prediction function is. We can compute the prediction error. This is going to be the prediction error, right? It's just the difference between the realization of the variable you want to predict and the function you apply to x's so that you predict y. Okay, so this is the prediction error. Yet we have not decided yet what p is. We just say that it's a function of x. X are random variables that we know, so that we see the realization of, okay? How do we pick the function p so that we have good prediction? Well, here comes the loss function, okay? So in some way, what's the loss function? Well, the loss function is a function of the prediction error, so a function of a, or if you want to write it fully, it's a function of the difference between what you want to predict and the function you use to predict it. And of course, if we have a sample, so we have many instances of y and x, we will have many instances of the loss function as well. And but if x and y, if we consider them random variables, well, they're random numbers in some way. So L will be, in theory, also a random variable, or in practice, if we have a sample, we will have many instances of L, okay? So this is not enough. Usually what we want to do is take the expectation of the loss function, which of course turns into the mean of sample data, and we want to minimize it with respect to the class of function we're considering. So P belongs to some functional class. I can just call it, I don't know, well, like F, a class of functions. The class of function can be all the so-called measurable function. In probability, measurable function, we can just define it as function that turn, if I know the x, then I know also the measure function of x, of the x. I don't want to give you formal definition. Of course, if you know probability, you know what a measurable function is. Otherwise, just take a measurable function, a function that makes any realization of the x's a number and not a random vector. Okay. So any well-defined function of the x. Okay, in some way. So basically, this is how we determine the optimal prediction function p. So in order to determine what's the optimal prediction function, we need what? A loss function. Okay. And the loss function is important because it defines the cost of your forecasting error, prediction error. Okay. If you don't have any, sometimes you use just standard loss function. So if you select L to be the square of the error, then you're minimizing the mean square error. Why mean? Well, because here there's a mean, okay? If you select the loss function to be the absolute value, well, you're minimizing the mean absolute error, okay? If you want to minimize, for example, the absolute error divided by, well, the real observation y, this is called the mean absolute percentage error. Well, percentage if you multiply it by 100, of course. Okay? So I can define many different loss functions. But usually the problem we have in mind, or the problem that our, I don't know, boss or the firm we are working for is providing us, usually they have also a real loss function. For example, in the book, I present this very example, which is something that actually happened to me and some other people from Bikoka years ago, when we had to build a model for predicting how many sunglasses, or actually, yeah, I think there were sunglasses, I remember many years ago, had to be produced. Okay. And in that example, which you find also in the book, we have a very asymmetric loss function. Now I explain you why. So let's try to I think I cannot remember the numbers during the book, but anyway, it's not that important. So example. Prediction of the number of sunglasses to produce next year. Okay. So let's see what kind of loss function we have here. Let's put some numbers. Usually, let's consider just the variable cost of producing glasses. So we condition on every cost that has been already done before going to production. So research in materials, I don't know, design research, marketing research, all that things already been paid. So we just have to decide. So we have the model of the sunglasses, and we have to decide how many sunglasses to produce next year. Okay. Let's just put some numbers. If I sell one pair of sunglasses, suppose as a producer, maybe I earn 50 euros. Probably in the shop you paid like 200 euros, but you have to take account there's somebody that distributes them. Of course, the reseller has to, the retailer has to also have his gain or her gain, and so on. So let's suppose we are just a factory, and if we sell one sunglass, so one sunglass or pair of sunglasses, pair, sells for 50 euros. Okay. Of course, there is a cost of production. Suppose we are, I don't know, it costs €1 to produce. It's not crazy. It's kind of this. This is the ratio. To produce a single sunglass is very cheap, conditional on all the investment you did in the past. So marketing, material, design, all that stuff being given. Producing the single sunglasses, it's very cheap. Let's just suppose that producing one sunglass, one pair of sunglasses, or producing. So this is selling and producing one sunglasses pair costs, let's say €1. Okay. Suppose that we have produced one sunglass pair that we are not able to sell. So let's put some expenses if we don't sell sunglasses, and we have to store it, and we have probably to, I don't know, to destroy it in some way, okay? So let's put like €1 more of storing, and no, questi sono costi variabili. These are variable costs. The fixed costs we already, they don't matter to us, okay? We have just to predict how many sunglasses pairs to produce next year, okay? So whatever has been done to design the sunglass, it doesn't matter. That's already been paid. So these are just variable costs. So if I produce one single sunglass, I spend €1. If I don't sell it and I have to store it and maybe destroy it, I have another €1, okay, to pay. Instead, if I sell that sunglass, I will earn, well, the €50 minus, of course, just €1, which is the production cost. So if I sell one pair of sunglasses, okay, I gain, so €49, right? So I get €50, but it costed to me €1 to produce, so I earn €49. If I produce one sunglasses and I don't sell it, cannot sell it, well, this cost me it cost me, well, €2, okay? Okay. So let's try to now think about prediction. So we want to predict how many sunglasses to produce next year, and let's consider the two errors we can do. So suppose I overpredict. So overpredicting means that my prediction, I call it, well, I just call y hat, is larger than the real value, which we don't know, but of course in 1 year it will be known. So if I overpredict, well, the cost for one single glass will be just, the cost will be just €2 times the number of sunglasses, okay? So for each sunglass that I have produced and I've not been able to sell, that cost me just €2, one to produce and one to store and then destroy. So my cost, if I overpredict one sunglass, will be €2. And of course, if I overpredict by, I don't know, if my error, this would be like so the error is defined this way, okay? I'm just using, I'm just using y hat instead of p, just because it's shorter, okay? So y hat is equal to p of x, okay? So this will be my prediction. So if I overpredict, well, my error will be the difference between the real one and the predicted one. If I'm overpredicting, this will be a negative value. So my cost will be minus 2 times euros, right? So this is, so I'm overpredicting. So this is going to be larger than this. Okay. So E will be negative, and my loss will be, okay, minus, because I have to make it positive, €2 per error. So per sunglass that I predicted and I didn't sell. Okay. So this is going to be the loss function in case of a negative error, right? So this is the loss in case of negative errors. So if I underpredict, it means that my prediction is lower than the real data in the future. Then, so if I'm underpredicting one single sunglasses, I'm losing 59 euros because I would have gained 50 euros. One is the cost, so I would have gained 49 euros that I will not gain because I didn't produce that sunglass that I could have sold. Okay. So in this case, the error is, in this case, it's negative. In this case, it's going to be positive. And in this case, for each sunglass I'm not selling, I'm losing, 49 euros. Okay, times, of course, the number of the error. So this is the loss under prediction. Or positive errors. So if I have to design this loss function, so this would be the error. If I make no error, I have no loss. So 0 is equal, well, 0 can be either. Of course, if I predict exactly how many sunglasses I'm going to predict, I have 0 error. So there's also a 0 error that implies no loss. Okay. So this I didn't consider, but it's very straightforward. And so if I have positive errors, then I have a very stiff loss function. When I have negative errors, I have a very, I don't know, flat loss function, okay? But anyway, the loss function in this case is made this way. So it's going to be, we said, minus 2n, or 2e, sorry, minus 2e for e negative, and 49e if e is positive. Of course, the 0 you can, doesn't matter. On one side or that one because it's 0. Okay. Does this look like well, we have to take, of course, the mean, so we will minimize, so we have to find the predictor that minimizes this loss function, which is very different than the square error, or very different than the absolute error, okay? So this just to communicate to you, the loss function depends on the problem. And there may be problems, this is a real problem that we had to solve, so we had to build a forecasting model, but then, okay, if you have a statistical model, you have the whole distribution of future observation of curves, you can minimize the loss function after building the model, okay? But if you use a machine learning model, which only minimizes a loss function, then you have to decide the right loss function to minimize. And in this case, if you use a machine learning model to learn from past information, whatever, this is the loss function you have to use, okay? So no mean square error, no absolute error, or whatever. Point 1. So what are the ingredients of making a point prediction, just point prediction? We need, well, a loss function, that's important. We need past information, or information on which I can base my prediction. I need a function of this information, and I need some samples in order to, of course, here I'm using the expectation symbol because I'm, where is it? Here I'm using the expectation symbol because I'm assuming these are random variables, but of course we will need some sample, and so the expectation will become just a sample mean. Okay, so we will have to minimize instead of the expectation. So this turns out to be like the minimization in real world problems with respect of the function of 1 over n times, or I that goes from 1 to n, the loss of ye minus pxi, or this is the sample, so this would be like e that goes from 1 to n, this is going to be the sample data. Okay. And of course, the expectation is just theoretical. This becomes a sample mean. Okay. And so we have to, this is what you do by machine learning. Of course, P can be whatever you want. It can be a linear regression, a support vector machine, and so on. Of course, the loss function is a neural network, but the loss function you have to fix so that it's meaningful what you're going to do, okay? What you're going to predict. Is that clear? Done up to now? So if we have probabilistic models, then, for example, if we pick a quadratic loss function, then this means that we are predicting with the conditional expectations. So if we have a probabilistic model of y given x, well, the quadratic loss function implies that our p, so our best predictor, is the conditional expectation of y given x. Okay. So usually, this means that usually what you're predicting with, because I would say most of your models, you probably use the quadratic loss function. So you're just trying to predict with the conditional mean. So conditional mean of the y given all the x's. So you've been doing that probably without noticing, but you're just optimizing to get the conditional mean of y given the x. For example, does anybody of you know if I pick the absolute value of the error, what is the optimal predictor? Does anybody of you know? So of course, this is a probabilistic situation. So what I know is the conditional distribution of y given x. I said, assume we have a probabilistic model of x given y given x. Okay. So in one case, we are just predicting with a conditional mean. If we pick the absolute value, we're using actually condition median. Well, I made it for median. So for example, if you're using a symmetric prediction model, meaning that the distribution of y is symmetric, well, then the conditional mean and the conditional median are just the same number. Okay. If y given x is doesn't have a symmetric distribution, then there will be different. Okay. This is going to be important when we will see some time series models, because sometimes, as some of you mentioned last time, it's more convenient to work on transformations of the data. Like, I don't remember who mentioned the logarithm. Sometimes we will predict, instead of predicting the original time series, we will predict the logarithm of the time series. And then in order to get back to the original matrix of the data, we have to take the exponential. But if you're using the conditional mean to predict the log of your time series, and then you take expectation, well, the expectation of the conditional mean are not the conditional mean of the expectation. So actually, you will not predicting with the same object if your loss function is different, if you're using the loss function on transform data. And we will get back there. I'm just anticipating some information we will provide later, just because I'm noticing, well, these things will be important also later. It's not just theoretical. As I told you, theory is needed for the practice, and practice will help you to understand the theoretical part. Okay. A nice thing, if we have such a loss function which is linear about zero, but if we have positive errors, it's got a slope, and then it has a different slope. If it's got negative errors, then this kind of loss function, they're also called pinball loss functions. Pinball because of the game. Pinball loss function generate percentile of the distribution, of the original distribution. So if I have, for example, this kind of loss function, suppose that, I don't know, loss function which is, I don't know, maybe minus a times e for negative e, or equals to 0, and plus b times the error for positive e. So I'm using this as an indicator function. This means this is going to be 1 if this is true, and 0 if this is not true. Okay, it's just an indicator function. So this is just like in our case, a was equal to, I think, 2, right? So a was equal to 2, and b was equal to 58. No, 50. No, sorry. Yeah, was 49. Sorry. Okay. So if this is the loss function, it's the pinball loss function, then we're predicting with sometimes we use this notation. So this is the quantile or the percentile of y given x, and tau, which is the percentage, is just given by b divided by a plus b. Okay. So a and b are both positive. They have to be both positive. And so if we select one of these loss functions, like the sunglasses loss function, it's called the pinball loss function, and it produces quantiles or percentiles. Quantiles, percentile are just the same thing. Okay? And so it's the percentile at percentage tau, where tau is given by b divided by a plus b. Okay? So in our case, we are predicting with, I don't know, it's 49 divided by 51, which is, I don't know, it's 0.9. I don't know. Anyway, it's a large number. It's very close to 1. Indeed, in that situation, it's much more convenient to overpredict than underpredict. Because if we overpredict, we are just losing 2 euros per sunglass. And if we are underpredicting, then we are losing 49 euros per sunglass. Okay. And so we will predict with the 90, I don't know, 5% percentile. So a very extreme positive value, much larger than the mean, because it costs much less over predicting than under predicting. Okay. here. I don't know, somebody of you can compute it. But it's anyway, it's a very, I would say something like this. And sorry, this would be the 98% percentile, okay? Good. That all clear what we're done up to now? If you have like the whole distribution of y given x, so if you build a statistical model, a statistical model is always a model where you have the conditional distribution of y given x, then of this distribution will you just get the 98% percentile. So it means probably you will have, I don't know, this is the distribution of future observations, so the distribution of y given the x. And you will, this would be the mean, which is optimal if your loss function is square. And this is going to be the 99% percentile or quantile. Okay, this here. So we want to overpredict. It's more convenient. In the long run, we save money by doing that. Okay. And there are many situations. For example, another one I can think of. Now it happens less often, but it was a time that Como Lake would, a lot of times, I don't know if anybody is from Como, but Como Lake sometimes would flood the downtown of the city. And of course, that cost a lot of money because a lot of shops, a lot of so houses and so on get ruined, and you have to spend millions of years to fix them. So suppose you want to predict the height of Como Lake in Como. And you have to decide, maybe you can act and say, in order to decide how much water I have to let out of Como Lake and maybe flood some field, some I don't know, agricultural fields in some way. I don't know how that works, but anyway, probably you have a cost for trying to lower the level of Como Lake that costs some other money because maybe you want to flood some agriculture fields or whatever. And on the other way, you have the cost of flooding downtown Como, which costs a lot of money. Again, if you can kind of estimate for, I don't know, for every ton of water, or I don't know how do you measure that, how much is the cost if you overpredict and underpredict, again, I'm sure you get a very asymmetric cost function there. And so predicting, again, the level of Como C using the mean, so that the conditional, the square loss function, it's not a good idea. So you may really come up with hundreds of examples of this way, okay? Of course, if you don't have an explicit loss function, for example, if you do economic predictions like GDP prediction or industrial production prediction, you don't have a loss function in mind. You just want to be as accurate as you can, but accurate, what does it mean? So usually you just use the quadratic loss function. There is really no good reason for that. It's just mathematical. The quadratic loss function is the simplest to treat. Because if you take the derivative, it's just 2 times and that it's linear, okay? And other loss functions like the absolute value of A, it's also symmetric, but it doesn't have a derivative at its minimum, so maybe computationally is not the best. So usually you go with the square loss function just because it's mathematically convenient. So if you don't have a loss function, okay, a very popular one, there are a good reason for that is the square loss function. That means that you suppose that your cost is increasing with the square of the error, which is also kind of a strong assumption. And it's also got some drawbacks because, for example, if you have outliers in your data, well, outliers will dominate the loss function, the quadratic loss function. Okay, so you have to keep in mind all the positive side and negative side. So mathematically, quadratic loss function is super. Outlier are very dangerous if you use least squares. So anyway, anything based on quadratic loss. So in that case, the mean absolute error is much better. Okay, because it provides you with a median. Think about a median. If you take one single observation, you take the most extreme observation and make it go to infinite. The median doesn't change, stays in the same point, right? So the median is just the central value, right? So you have the same number of values on the left and the same the number of values on the right of the median, right? If you take the most extreme value and make it go to infinite, the median doesn't change, okay? So it's very robust to outliers. So for example, so in that case, if you think you have in your sample possible outliers and large outliers, then maybe the quadratic loss function, even if you don't have an explicit loss function given by the problem, don't choose the quadratic one because it's going to be very sensible to that. Choose the absolute error. That's going to be sensible to a large number of outliers. Okay, so I'm trying to make this reasoning because you've been using those things without reasoning, I think. I think nobody has been explaining this thing to you before, right? But you've been using loss functions as they were like the most natural thing to use, especially in machine learning. And usually, for example, when you design a neural network, you can choose whatever loss function you want, okay? So you can think about either the problem or the consequences if you use like a quadratic loss function. Good. Well, of course, in time series analysis, which we are going to do, if we choose a quadratic loss function, as I told you, usually we deal with the conditional expectation of y given x. In our case, y will be future observation and x will be past observations, okay? And you kind of need to be acquainted with some of the properties, the main properties of conditional expectations, because they're important to derive results. Well, for example, I didn't mention this in the book, but I just mentioned it before. If I take, if g of y is a nonlinear transformation of the data of y, well, then the conditional expectation of the transformation is different than the same function applied to the conditional expectation. Okay. It's important to remember because sometimes, as I told you, we will predict using maybe a transform of the data, and then we want to go back. But then we have to keep in mind that we will not have the conditional expectation if we apply the same function. Okay. Suppose we are predicting the log of our time series. Then I take the expectation, the exponential to go back in the same matrix. Well, I no more predicting with the conditional expectation of the original data. Suppose this is the original metric of the data, even the best, okay? As I told you, this will come later again, but it's good that you remember that. We even know the direction of the inequality. It can be negative or positive according if G is concave or convex. It's called Jensen inequality. So you can check on Wikipedia. So for example, if we take the exponential, so if G is the exponential, so we have predicted So this was the log of our time series, and so we want to transform the exponential. So we just take the exponential of the prediction. So this is our prediction in log. We take the exponential. Well, this is going to be smaller than the real value, which is the one we are interested in. So this is going to be smaller than this one, because the exponential is convex. If you don't remember concave and convex, concave is easy to remember because it reminds you of a cave, okay? So concave, convex. Good. Other properties, well, the conditional expectation is linear. So if I have like the conditional expectation of, this is just the sum of the two conditional expectations. An important property is called, so this is linearity, is that, for example, if you predict with a conditional expectation and then you compute the prediction error, this is going to be orthogonal, where I use orthogonal with the sense of uncorrelated to any function of the x. So this is your prediction error, right? And this is any function or all function of the regressors, the features, whatever you want to call. Okay, and this is going to be 0. So this is an important property of the conditional expectation. So whatever the transformation of x you get, you may want to compute the correlation or the covariance between the prediction error and any function of the x, which is the one that you'll be using for predicting, will be always 0. In some way, it means that you're using very well your information. There is no way to make a better, of course, according to correlation, better use of your information. Because if there were some correlation, it means that then I can make a better prediction, because I can exploit the correlation to make my prediction better. But if I measure in some way the orthogonality by using the correlation as we do here, well, this is the covariance, but of course, 0 covariance means 0 correlation. It means that we're doing a very good job. So this is a very important property. I call it orthogonality to the x. And then another very important property you should know about conditional expectation, it's called the law of iterated expectations. And it means that if I compute the expectation of the conditional expectation of y given x, this is equal to the expectation of y. So first of all, realize that the conditional expectation is actually a random variable. Why is that a random variable? Because x is a random variable. So if x is random, so it's like if my regressor is random, then also the prediction is random. Of course, when I see the x, so when I see a realization of the x, then that's going to be a number, and then also the conditional expectation will be a number. But in abstract, y given x is a function of x, of course, and x is a random variable. So a function of a random variable is random variable. And being this object here, random variable, I can take the expectation. And what's the expectation of the conditional expectation of y given x? It's just the expectation of y. This is also important. In many time series models, this can solve things that seem complicated in a very easy way. I can sometimes pretend to know something I don't know, But I find out, for example, that a conditional expectation of y given x is a constant, then I find out also that the expectation of y is a constant, is equal to that constant. Okay? So this is called, usually it's called the law of iterated expectation. Okay, so I guess who studies statistics in bachelor probably should remember this property of the conditional expectation. Otherwise, you find also some more in the book, maybe listed in a better way than my notes here. But these are important properties you should keep in mind. Maybe if you come from computer science, you haven't seen this yet. Then one more step. Let's suppose that. So suppose we take only the class of linear prediction function, meaning that the prediction functions of the data is something like, well, a constant plus the vector of beta times our vector of beta. This is the family of linear functions in X. Okay? Then, if we use a quadratic loss function, if we use, let's make it short. If we use quadratic loss function, then we get the linear, this called linear optimal predictor or optimal linear predictor, which usually in the book I use this notation just to remind kind of the expectation. It's not an expectation, it's a linear prediction. This is not universal as the expectation symbol. So take it as more, it's pretty much used, but it's not so universal as the expectation symbol. Anyway, so the best linear prediction of y given the x, and actually we could even have a vectorial y. So we are predicting many y's, not just one. Doesn't really change anything. It's a well-known formula that everybody should remember. So this could be also a vector because I told you also y could be a vector of variables I want to predict linearly in X, where this is the mean or the vector mean of y. This is the mean of the X. And this is the covariance between y well, minus its mean and x minus their mean transpose. Okay, and of course you can substitute x, dy with the x and you get this. So this is the covariance matrix of the y's with the x, and this is the variance matrix of the x. Okay. Yes.
covariance of x minus 1?
Yeah, it's the inversion of the matrix. Yeah, these are matrices because, well, this is always the matrix. Unless you just use one regressor, this is going to be a matrix always. And again, we can define this even if we have not just one y to predict, but a vector y. It doesn't really change. So I give you the general formula. And of course, in this case, we are minimizing the mean square error of each y. So y1, y2, y3, and whatever. Okay. So because the formula works also if y is vector. So let's just define y to be possibly also a vector. Okay. So this is a vector. This mu of y is a vector. This is in general a matrix. Of course, if you take one single y, this is going to be scalar, and this is going to be a vector. But otherwise, this is in general. And this is a matrix you invert. And if it doesn't invert because it's not invertible, actually, you know that in non-invertible matrix, I mean, the name non-invertible is not very good because you probably know that in non-invertible matrix has infinite inverses. It's really not invertible. The problem is that it has too many inverses. So if this still works, even if this is not invertible, if you just stick one of the possible inverses. So it's so-called generalized inverse will apply. Okay. When does that mean? What does it mean if this is not invertible? So if this matrix sigma x is not invertible, what interpretation can you give about that? In some way, it means that some variables are linear combination of other variables. So it means you're giving the same information more than once. And so of course, the solver is not able to say, okay, you have to put a coefficient of 5 to x1 and a coefficient of -3 to x2, because you can find an infinite combination of coefficients that will give you the same prediction, because you're actually putting twice the same information. Okay. So that means if it's not invertible, it just means that you're using twice the same information. But anyway, the prediction will not change. You can even put many linear transformation of the x's. If you use a generalized inverse of the x, you will get the same prediction. So the prediction is actually unique. Okay, even if the matrix sigma xx is not invertible, but the prediction will be the same anyway. Okay? So the prediction is unique. Yeah, the nice thing that you probably are not noticing, but in here to make you notice, here we really don't need the distribution of y given x. We just need the mean and the covariance, and that's everything I need. So that's why our linear predictors so much used, because they are really in some way non-parametrics. I really don't need to know much about the distribution of y and x or y given x. I just need to know the mean of y and x and the covariance between the y and x. And all these things I can, of course, estimate really easily with the sample covariance. Okay, I just use the law of a large number. We know that all these things, if I use the sample version of all this thing here, I'm going to have a consistent estimation of this matrix and also on the mean, if you're just using sample means and sample covariance. So actually, I really don't need to know anything about the distribution of the data. So that's why linear predictors are very much used, because they need much less information than optimal predictions. This is, of course, all true under quadratic loss function. If I have non-quadratic loss function, then I, again, need the distribution of y given x, even if I just use linear prediction. Finally, I even know, these are, I think there are a few formulas that students of statistics or data science should know forever in their life, but this is one of those. So here. So this formula here, you should kind of know for all your life. I think it's important. This is just like a regression function. It's a linear regression function. And even more than that, we can straight away compute the mean square error that we are committing by using this prediction. So the mean square error of using these linear predictions is simple. It's just the variance of y, or the covariance matrix in case we have a vector y, minus the covariance of y and x. Then there's the inverse of the sigma matrix, and then you have again the covariance of x with y, which is just the transpose of the covariance of y with x. So if we use linear predictors, we also know what's the average error I'm going to make. What by average it means the error I'm going to make. So if I'm predicting with the linear predictor, this is going to be the error I'm going to. Of course, if there is no correlation between the x and the y's, well, then there is no prediction. You notice that if there is no covariance between x and y, then this is equal to 0, and there is really no prediction other than just the mean of the y. Okay? And of course, if there is no prediction other than the mean of y, then you get just the covariance of y. So this minus sign, which many students for some way mistake and make a plus, it has to be a minus, because if you're predicting, you're doing better than just using the mean. If you're doing better than just predicting with the mean, then you have to take something off of the variance of the y, because you're explaining part of the variance using the x's. Okay. Okay. Again, you will find in the book some of the properties of linear predictors. For example, linear predictors are linear, as the expectation. We also have like a result, an orthogonality result here, but it's not as strong as the other one. In this case, the orthogonality is just with the x, or linear function of the x. So the expectation, or which in this case will going to be the covariance of the prediction error when you predict y using the linear predictor, times x, and in this case, this is going to be transposed, is equal to matrix of 0. Okay. So what's the difference? Here we are only using linear information of the x, so the incorrelation between errors is only with linear function of the x. Okay. I just put x. Of course, any linear function will do, because if I multiply it by a vector, this doesn't change. Okay? If you go back to the expectation, to the conditional expectation, it was any function of the x. Here's only linear function of x. So I'm just using the linear information. This helps you to understand what are you doing more when you're considering machine learning models with respect, for example, than a linear regression. In a linear regression, you're just using an information of x linearly. But if you use a nonlinear function of x, you may get more correlation you can exploit to improve your predictions, okay? While if you're doing a machine learning model where you predict by using any function of the x, then you're probably going to be a good approximation, to have a good approximation of the conditional expectation, and then you're probably orthogonal to any transformation of your data x, so you cannot improve your prediction method in any way. Okay, so when you have, for example, we will see very quickly that a very important function of time series we are going to consider is the so-called autocorrelation function. So the correlation of yt with yt minus 1, yt minus 2, and so on. if the autocorrelation function is 0, it means there is no way you can predict better than the mean of y using its past. But that doesn't rule out nonlinear models, so machine learning models, because correlation is talking to you only about linear prediction. Okay. Of course, we'll come back to that as well. Okay, well, you will find also other interesting properties of the linear predictor, for example, a way to update it if you get more information, so on, in the book, but you don't have to know them by heart, since they're important. So these are the, one more thing about this. There is one situation, actually more than one, but a very important one situation in which the optimal predictor and the linear predictor under quadratic laws are the same thing. So if your data, so let's stack your y and your x in one vector, if you can assume they have a normal distribution, okay? If we assume they're jointly normal distributed, then I don't know, if you remember what's the conditional distribution of y given x, well, the nice thing is that the normal distribution is close to linear combination. So if you take any linear combination of this vector, you still have normal observations, but it's also close under conditioning. It means that y given x is going to be again normal, and the mean is going to be exactly the linear predictor. And the variance, well, I'll write it down here, is going to be the mean square error of the linear predictor. Okay, so in case we have joint Gaussianity, well, linearity is the best you can do, meaning that the linear predictor is also the conditional expectation, so the best predictor under square laws. Okay? Again, if you know, I mean, if you remember the other formula, well, it's also the formula of the conditional expectation of the normal, which is another formula everybody that studies statistics should know. Okay? Actually, there is a larger class of functions for which the mean is exactly the linear predictor. They're called elliptical distribution or elliptical random variables. But the only elliptical distribution for which the variance doesn't depend on the conditioning point is normal. If you look at the variance, it doesn't depend on x. I mean, of course, the mean depends on x, but the variance or the covariance matrix doesn't depend on x. It depends only on the covariance between x and y, x and x, okay? But it doesn't matter to what point I'm conditioning to. This changes, but it doesn't change. And the normal distribution is the only distribution among this elliptical distribution where this holds. All the other distribution, the variance will depend on the x in which you're conditioning. Okay. So, a bunch of theory about prediction, but I think I give you some. I mean, if you are not acquainted with this thing, I think I give you maybe a lot of information in one place. Some of you probably just are reviewing this. I hope this clarifies the connection between loss functions and predictions. linear models, nonlinear models. And we will actually use many of these things while digging out in time series analysis, because many of these results will be used in time series analysis. Of course, if you read the first chapter of my book, it's kind of more deeply explained, and there are also proofs for everything that I'm showing you. You don't have to know the proofs, but if you're curious, they're not hard. They're really simple proofs, actually. Good. Yeah, this is basically the theoretical part I wanted to go through, and now let's just play a little bit with R and some data. As I mentioned last time, I think it could be a good idea to take that famous time series where I showed you last time. There are passengers just because it's there. So our Y is going to be the air passengers, which is already in R. We already seen that last time. Probably if you already had some kind of time series course, you already know this time series. Last time I told you, I want you to build a prediction model for this time series. Maybe we can leave out the last year. We pretend we don't know the last year of this time series. We want to predict that. And the only weapon you have in your hands is a linear regression, okay? So I will be using R. If you want to use Python, you're free to do that. Otherwise, the only weapon here is ln, okay? And of course, you're free to produce whatever features or regressor, how you want to call it. You're free to produce them. So feature engineering is the main thing here. And so try just to build, think that you're just being hired by some firms, and you told you, okay, we have this time series. I want you to predict this time series. And everything that I can give you is Excel. Okay, in Excel you can do a linear regression. So, okay, we will not use Excel, but we still pretend we only have a linear regression as a tool, okay? So we can, I mean, you can work alone or we can reason together about some solution. How would you, a couple of things we already said last time, but how would you suggest to build the features, so the regressor, in order to do a linear regression and predict Y in this last year? So let's like eliminate. We can do this way. This is a TS object, so a time series object. I think it goes up to year 1960. So we can set to 0 everything from the 60s January till the end. I think this should, no, to NA, sorry, missing. Okay. Okay. Now, Y doesn't have the last year. We want to predict it. Or we can just throw away the last 12 observations, whatever. Maybe we should just throw them away, sorry. Just, I think it's from 100 and, yeah, 123, right? Oh, sorry. Stupid. Okay. So this is a better way. Well, and okay, of course, now it's no more a time series object, it's just a vector. It doesn't really matter because anyway, the LM doesn't keep in mind if it's a time series object or just a vector. Now, probably, do you know there is a time series object in R? Probably not. Okay, in R, you can, there is a native time series object, which is TS, which is a really stupid, simple kind of object. It's fine if you have like monthly time series, quarterly time series, and so on, because it just manages one counter, which is usually the year, and the periodic counter, which is usually the month or the quarter. And you can, for example, see the air passengers is already a TS object. Well, you can check it by class, but you also notice it because it printed this way. Because it knows that there is a slower counter, which is the year, and then if you put 12 as a frequency, then it assumes it's a monthly time series and will print this way. Okay? Just check TS, so question mark TS, and it's very simple object. At the moment, it's not our point. We will learn also how to deal with the TS object, but actually there are much better time series objects than the TS. For example, we use often a package called XTS, so extended time series, which is much more complete. Because, for example, if you have daily data or even hourly data, the TS object is really not able to deal with it. It just deals with yearly, monthly, quarterly time series, I would say. Okay? But at the moment, I don't want to. We're just starting to think about how to solve prediction problem or forecasting problem. So at the moment, it really doesn't matter if we have to do with a time series object or just with a vector. When I did this, I just transformed implicitly the time series object into a vector, a regular R vector. So Y is now just a vector. Okay? And you notice that because the plot function doesn't plot a line plot, but it plots a dot plot. You can, of course, impose the line plot doing this, but now you don't see any date here, you just need the sequence because it's no more a time series object. Okay, it doesn't really matter. Let's start reasoning about this time series. How would you predict this? First of all, would you predict this time series or some transformation of this time series? We talked a little bit about that last time. We have a linear model, LM is for linear model, so it's an additive model. Whatever we do, we are not going to be able to generate this kind of multiplicative ratio or rationality of this time series. It's like we have a trend, and the trend kind of is multiplied by a seasonality factor, which is when it's larger than 1, will increase our trend to bring us to, for example, July or August. Or if it's below 1, for example, 0.9, it would bring us to, I think this is November or something like that. This cannot be an additive time series because we see that the seasonal variation increases together with the trend, and we are not able to model that using a linear model, right? We talked about that already last time. So what transformation of the data will you suggest to work on? Nobody talks. Last time you were talking. Well, the exponential function is what brings us from additive to multiplicative, but here we want to go from multiplicative to additive. So what transforms a multiplication into a sum? What kind of transformation brings you from the logarithm? Yeah, we talked about that last time. So first of all, we will not predict y in the first place, but probably log y, okay? Last time we saw that. Now you see that the seasonal variability, but the variability in general of the time series is kind of constant all over the time. So if we have like, if we build a component for the trend and add that component to a component for a seasonal variation, then the seasonal variation will be similar every year. In the other time series, the original time series, it's like last time I already explained you, here we kind of have like a trend that multiplies a seasonal factor that goes beyond or below 1 and generate this variation. Of course, the variation is larger when the level is larger. If this is 100, as I say, if I multiply by 1.2, it means it's 20% higher. 20% higher, of course, is a much greater difference between the point and the level. If we have a level of 100, that is, we have a level of 10. 20% more of 100 is 20. 20% more of 10 is just 2, okay? So this is a multiplicative time series. We see that because the trend and the variability, they grow together. And the log, the natural log, but not just any log, but we usually use the natural log, is able to transform a multiplicative time series into an additive time series. So as I told you, in a machine learning model, that doesn't have to be a problem because they are non-linear machine learning models. We have other type of problems. We already mentioned this type of problems also last time, but we will go back to the this how to use machine learning models on time series in this last third of this class. And now we made the time series linear. I mean, there's a trend, there's a kind of constant variability around the trend. Okay, the first problem we have solved. Now we have to build features to meet the features of this monthly time series. This is a monthly time series. It means that, okay, we have a trend, but we also have some movement that kind of repeats itself every 12 observation, because this is the number of passengers in American Airlines. You see that they fly the most on July and August. They probably fly the less on November and so on. So how do we fix these two features? So a growing trend and a monthly seasonal components. What kind of regressors or features would you build for this? You have to keep in mind we're just using a linear model. The features we build here, of course, they're probably different than the feature we would build in a machine learning. Okay, we will reason about that later. Now we just have a linear models, because for a while we will just have to do with linear models. Okay. So first of all, what would you use for the trend? A straight line. So something that counts. Okay. So maybe let's just build, I don't know, we can call it trend. Or actually it's more like a counter. So like counter. For example, it could be a counter from 1 to, okay, if we want to keep also some of the counter for the prediction, we can let it count up to 144. And then we will just use the first 120 observations for the regressor, for the regression, and the last, actually, 24 observations. Yeah, we kept just, okay, we threw away 2 years, not just 1 year. So we threw away 2 years that we want to predict. So I'll build also the regressors for the missing 2 years we want to predict. And of course, in the regression, we will just use the first 120 months, okay? So this is just the counter. Okay, we can start by just regressing log y on, I have a problem, I don't have the tilde. I know where to steal it. And you probably know that you can just get the tilde with Alt 96. I don't have any numeric keyboard, so I can steal it from here. Yeah, the Italian keyboard doesn't have that. It's here. Oops. Okay, let's just call this reg1 maybe. So if we plot log y and the in-sample prediction, which you find inside reg1, it's called fitted values. Maybe just give a red color. Okay, this is just a linear trend. Maybe we can just. And so we kind of fixed the trend. Of course, now we are doing just a deterministic model. It would be a model which is okay for this time series, which is a very regular time series. We're just starting with a deterministic model. Then, of course, we will move to stochastic models gradually. But all the reasoning we do in a deterministic model, you keep it in mind because it will be very useful also in stochastic models. Okay. Okay, it's fine. Maybe we could even use a quadratic trend that fits a little better, maybe in the last part. I think it's kind of overshooting. If you look at this trend, probably the trend is kind of getting slower than linear at the end of the time series. So probably a quadratic trend would do better than a linear trend. But let's just stick to the linear trend for the moment. In order to build a quadratic trend, we're still using a linear regression because we just need a new features, which is the square of the counter. Okay, but it's still linear regression. So I can take any nonlinear functions of my features because anyway, I build the features. Okay, but we didn't fit the seasonality of this time series, and the seasonality, of course, moves a lot of this time series. What do you propose for the seasonal parts of this time series? How would you fit that? Kind of regressors. There are many solutions actually, but one is very simple. It's very straightforward. You've done 1 year of data science. You have to come up with ideas for this. No clue how to model. What? Yeah, we need to fit the seasonality. Go ahead. Yeah, that could be a solution. That's the second solution I wanted to show, but we can start with that as a first. Of course, we can use we have a periodic function because the seasonality is a periodic function. Actually, it's a periodic function with mean zero. Why with mean zero? Because if I sum the values of 1 year, the seasonality has to disappear. So, for example, if I add the GDP, for example, the GDP is a quarterly time series. So I have 4 observations. And of course, there's a lot of seasonality. If I compute the annual GDP, I have to sum the quarterly GDP over 1 year. And so the seasonality has to disappear. It means that I have to sum quantities, seasonal quantities that in 1 year just sum to 0. So the seasonality should be a periodic function of period, in this case 12, with mean 0. Okay? So sine and cosine are a solution. Let's go like she suggested. That's a good idea. That's probably not the simplest one, but it's probably one of the most useful. So very short theory about that. So suppose gamma t is our seasonal component. it's a function of time. Of course, we're working just with integer time. So we are not in continuous time, we are in discrete time. So t is just an integer number. And so usually functions of integer number we write like this. So I told you, what's the seasonality? Well, the seasonality, it's a periodic function of period. In this case, 12. In general, we can call S the seasonal period. So how many observations in 1 year, for example, we can observe? So periodic means that gamma of t must be equal to gamma t minus s. At the moment, it's just a deterministic function. And the second property that I just mentioned is that it must sum to 0 or mean to 0, but sum to 0 is the same, if I sum over s subsequent times. So I would say gamma t plus minus 1 plus etc. gamma t minus s plus 1, this has to be equal to 0, okay? So there are many ways to fit such functions or to build such functions. She suggested to use cosine and sine function, and that's fine because we have this result. We can call it like a discrete Fourier. In this case, it's a representation of the seasonality. Any function with these properties, you can write as sum of j that goes from 1 to s divided 2 integer part. So this is the floor function, so the integer part of, let's say, aj, which is a coefficient, times the cosine of, well, let's just write the frequency this way, and then I will tell you how to compute this frequency, plus bj sine frequency lambda j times t, and the frequency is defined by 2 pi divided by s times j, okay? So this is a result. It's equal. It's not an approximation, it's just a representation of such a function, okay? So you can represent a periodic function of period s and mean 0 as sum of sine and cosine at given frequencies. These are the frequencies we're considering. Sometimes this is called the frequency. Sometimes the frequency is called module 2 pi. For example, engineers usually call frequency this without the 2 pi. Doesn't matter. Okay. And what does it mean? Well, that I just need to build 6 cosine and actually 5. I will show you why 5 sine features. And these are known. This is our counter, and these are known frequencies. So these are all functions that I can compute on the data to build new features. Okay. And of course, the regression coefficient that will be estimated by the LM function. Okay. So these are just new regressors, many. So just notice one thing. If s divided by 2 is an integer, so is equal to s divided by 2 integer part. So if s is even, okay, then the quickest cosine functions, so if j is equal to s divided by 2, if we take the sine, we have the sine of 2 pi divided by s times j, but j is just s divided by 2. So this simplifies, but we have the t, and we have the sine of pi t. Well, where t is just an integer number. So what's this number here? It's actually a number, it's not a function. So you have the sign, of, so you have, if t is equal to 0, it's sine of 0. What's the sine of 0? 0. If t is 1, you get on the other side of the circle. And again, you're again on the x-axis, so the sign is again 0. Then you have 2 pi. 2 pi, you're back at the beginning. So again, it's 0. So this is always 0. Okay. So actually, you just need, in case you have an even s, then you have to throw away the last sign because anyway, it's always 0. So you will always have s minus 1 cosine and sine function. So because if s is even, we see that we have to throw away the last sign. If s is odd, for example, suppose we have daily data and we want to model a seasonality every 7 days. Then we have 7 divided by 2 is 3.5. Then I take the integer part, it's 3. And then I have 3 cosine and 3 sines, which is 7 minus 1. Okay, you always have s minus 1 cosine and sine function, or new regressors, new features you have to build. Okay, and this is a way to build a seasonal component, which is very interesting because the frequencies here are ordered from the lower to the higher. What does it mean? That the lower frequencies mean smoother functions, so smoother cosine and sine functions. So they move very slowly. The higher J, so the higher the frequency, the rougher becomes the sine and the cosine function. So we have a naturally ordered from a smooth to rough set of functions. If you have to approximate maybe just a smooth seasonality, think about, I don't know, daily data, a daily temperature data. So a mean temperature of every day in Milan, for example. Well, probably you just need one sine and cosine pair because the temperature, the average temperature is governed by the season, okay? And so probably we just had a very warm summer, a very cold winter, and we just the first pair of cosine and sine function, you get the whole movement. You don't need 365 divided by 2 integer part cosine and sine function. You just need probably one, the smoothest one, okay? So if you have a smooth varying seasonality, probably you can throw away many high frequency cosine and sine function. And that's very good for modeling high frequency data. We will see that later on, for example, with electricity demand data or electricity price data, or I don't know, highway congestion data and so on. They're hourly data actually. And in order to model a very long seasonal component, like within year seasonal component on hourly data, then we would probably stick to just few cosine and sine function. We will not need to use all of them. Okay? We will, again, come back to that as well. Let's try to produce these features using R. In R, there is a very convenient function to do that. It's called outer. I don't know if you ever use outer. Outer takes 2 vectors. Well, it doesn't have to be 2 vectors, but let's say 2 vectors and then a function, and a function that takes 2 parameters, okay? And it applies the function to, let's say, the Euclidean, for how do you say, the Cartesian product of all the, so the first element of the first vector with the first element of the second vector. The first element of the first vector with the second element of the second vector, and so on. It applies the function to all the combination of elements of the first vector with the elements of the second vectors. Usually the second function is the product. In our case, we will not just need the product, but of course you can provide also other function of 2 arguments, and it will apply that function to the all the combination of the x elements and y elements. So For example, let's go on here. We can start with building all the frequencies that we need. So if you look at this, we have t that goes from 1, t is our counter variable, it goes from 1 to 144, and then we have j, and j goes from 1 to 6, because we have a monthly time series, right? So our j is from 1 to 6. So we want to do the product of, so we take the vector of t's and want to multiply that vector of t's to the vector j's multiplied by 2 pi divided by s. So we can call this the frequencies time t. It will be frequencies time t. And we can do this with outer. Well, you see there, you have x, y, and then a function. And the default function is the product. And so we pass counter, for example, as for the t, and then we pass a vector that goes from 1 to 6, and then we multiply by 2 times pi divided by 6. So this is going to compute all the lambda j times t. So what we're going to produce is lambda j times t, which is just 2 pi divided by s times t times j. Okay? This is exactly what we're producing here. Okay? Whoops. Counter. Okay. You see, it's a matrix. Here we have the time. On the rows, we have the time, the passing time. And here we have the j's. So the first j, the second j, and the sixth j. Okay? Is that clear? So I'm just computing this thing here, which is the arguments of the generic cosine and sine. Okay? Is that clear? Of course, now I have to build the cosines and the sines. We can call, I don't know, the matrix of cosines, which is just the cosine computed at those frequencies and times. And as for the sines, we do the same thing. We can call the matrix SI. But here, remember that we have to throw away the quickest frequency. Well, I can compute it, and then we will see that actually the quickest frequency is just zeros. Well, it's not exactly 0, but it's numerically 0, okay? Because of course, everything is approximating a PC, in a computer, but this is actually 0. So this we can throw away. So what we can do is just say, okay, I don't want the 6th frequency here. And if you want to see what we have just created, for example, there is matplot. This is the cosine function. Well, maybe let's just pick one year. Otherwise, it's too noisy to understand. So this is just 1 year of data, and then they just repeat because it's periodic. We have a problem. There's this purple. I see this purple line, which is kind of strange. Why is this equal to 1? Repeat this. Questo non c'è. No, there's something wrong here. Sorry, 12, not 6, 12. S is equal to 12, not to 6. 6 is the half, the half of 12, sorry. So now it's correct. So this is the cosines, and of course the sine will be just the same, but shifted. Okay, so the black one is the lowest frequency cosine. Indeed, it takes 1 year to complete, makes a whole movement in 1 year. Then the second frequency is the red one, which makes 2 movements in 1 year. It's the red dotted one. So it makes 2 whole movements in 1 year, and so on. And the same thing holds for the sine function. Of course, the sine function are just the same, but they are just shifted by half year. Okay. Now we can estimate the second regression. Maybe we could just for making a more ordered thing, we can just bind all these features in one matrix. So we put the counter, we put the cosine and the sine, and then we regress y on, sorry, I have to steal this, or log y actually, log y on x from 1 to 120. Okay? For example, let's see the output of this regression. Yeah, I made the text very large, so you can see it quickly. Wait, I'll try to make more space. Okay, so let's comment on this. So this is just a linear regression on a counter, and then all this sine. I could have put the names. Maybe you can use the name cosine. So anyway, so this is the intercept. This is the coefficient of the trend, which actually, since we're working on log, you know, log makes everything relative. So actually, this 0.01 is approximately 1% of growth every month. If you take the log and take a small change, then that's approximately a rate of growth. Okay, I can show you why. But so it means that every month this time series grows by approximately 1%. And it's funny because it's additive. You know, it's usually you cannot add index numbers and so on. You have to multiply them, so the returns, for example. But in this case, there are log returns, so you can sum them. It means that in 1 year, this time series on the average grows by 12%, approximately. Okay. Maybe, as I told you, it would be more useful to give some name also to the cosine and sine, so we have clear pictures. So call names of co, we can put paste cos from 1 to 6, and we can do the same thing with the sine regressors, so we can easily recognize them here. 5. Okay, now we also have the names. And as you see, we have, well, these are the coefficients of the linear combination of cosine and sine. Some are significant, some are very close to 0 and probably not significant. Of course, I wouldn't trust these statistics too much because we are in a time series context, And if you remember what are the basic assumptions in linear regression, we're probably breaking them. So I wouldn't trust these p-values too much. But anyway, let's pretend they're good p-values. For example, we could throw away the cosine number 5 and the cosine number 6, which are very rough moving cosine functions. They are the one that move the quickest. And for example, as for the sines, actually we keep the quickest sines. Maybe we could throw away the third sine and still have a good representation, parsimonious representation of the seasonality. But anyway, let's see if it worked. Let's plot the log time series. And let's plot the fitted time series. Maybe red. Oops, what's the problem? Oops, terms, no. I wanted fitted here. Okay. Okay, you see that now we are also modeling the seasonal variation. Of course, it's deterministic, meaning that we don't allow any change in time of the seasonality. Seasonality may change in time, okay? We will learn how to let that happen. But at the moment, we have simple moment. Actually, the seasonality is not bad at all. What is a little bit bad, in my opinion, is the trend, because as I mentioned, it looks like we're kind of overshooting. So the red line is at the end is kind of higher. So I expect our prediction maybe to be overshooting the real data, because it looks like the trend is likely growing less and less quickly. Okay, so probably quadratic trend would do better than this. But what I wanted to show you is that actually this sine and cosine function are great for modeling seasonalities. But they're not the only solution to the problem. Cosine and sine function are great in order to be parsimonious if you have a smooth, as I told you, smooth seasonalities to model. Suppose there are abrupt seasonalities. Let's suppose this extreme example, which is kind of true if we take many Italian data. In Italy, nobody works in August, okay? So any economic time series would drop down in August. So if you take industrial production, I have put industrial production in the data you find in the e-learning page. Suppose that you have a monthly time series which has always the same value, but on August where the value drops down by 50%. You can still use cosine and sine function to model that, but you probably will require all the 11 functions. But actually, you can fix that with just one function, with just one regressor. How would you fix that? Suppose monthly time series, apart from the trend, all the values are the same, and then it just drops every August. Right. One-hot encoding, a statistician called that dummy variables. One-hot encoding of the month variable is just building a dummy variable for every month. That's what I thought would be an easier solution for you to think. But she came right away with a more complex solution, which is very powerful. So that would have been my second proposal to you, but I didn't expect somebody to propose that. I expected many of you to propose dummy variables or one-hot encoding of the date of the month, which is very simple. There is only one little problem. I mean, from the forecasting point of view, it's really not a problem. From the modeling point of view, it's a slight problem that one can correct. Suppose we use one-hot encoding of the month. So it means we create one variable which is 0 and it gets a 1 on January. Then there is a one variable that is always 0 and gets 1 every February, and so on. We're respecting this property because every variable, well, of course, we will take a linear combination of these variables. So the linear combination of these variables will respect this property, so the periodicity, but this will fail. It's not a big problem. We can fix this. But remember that if you, for example, while sine and cosine are great to do this, I can already separate the trend from the seasonality. How can I do that? For example, I build the trend by just multiplying the counter times I take from the regression the second coefficient. So the first coefficient is the intercept, and the second coefficient is the slope of the trend. So this is going to be our trend, right? So we have the intercept plus the slope of the trend times the trend. Okay. What about the seasonal component? Well, this is we have to take. We can take the matrix X, throw away the first variable, which is the counter. So we have all the cosine and sine now, and we multiply using matrix multiplication by the coefficient, the right coefficient. So we have to throw away the first two coefficients. One is the intercept, and the other one is the slope of the trend. So we can just throw away the first and the second. Okay, so we are multiplying the cosine and sine functions in the matrix, or variables in the matrix, times their coefficient, right? And this is going, oops, incorrect number of dimensions. Why? Sorry, this is a vector, not a matrix. Okay, so okay, this is just the seasonal component. It's periodic, it's got mean 0, okay? So we are summing the linear trend, what we call the trend, to this one, and we get the prediction of our time series, okay? And as I told you, this has no effect on the trend because it has a mean of 0 every, if we sum 12 subsequent observations, right? I just picked up, is it clear what I'm doing here? Maybe not. So let's write down a little bit what we're doing. I hope this simplifies. So what we did is we have built the variable t time. We call the counter. I didn't call it t because there is a t function in R. I didn't want to override that. Okay, so this is our counter variable, and then we call it, well, we have cos from 1 to cos 6, and then we have sin 1 up to sin 5. Okay, these are all our variables, and of course there is an intercept. So we're saying, okay, our prediction is just an intercept plus the trend plus, and then we have, like, let's see, I call it A1 coefficient times the cos1 t, then A2 coefficient times cos2 t, and so on, until A6 cos 6 t. And then we have the sines. So let's say B1 times sine 1t, and so on. So this is the model we just estimated. Or if you want to see it like a typical regression model, this is like a mean zero error, okay? So we just estimated this model. Well, the nice thing is that, where is the trend here? Well, this is the trend. And where is the seasonal variation? Well, the whole thing here is the seasonal component. Oh, sorry, it's without this. So this one is the seasonal component. So what I just built, I built this one, which I called the trend. I've just used R to, this is the intercept, and then this counter times its coefficient. So beta 0 is this thing here, and beta 1 times t is this thing here. And then I did the same thing to obtain the seasonality. I multiply every single variable, their coefficient, and sum them all. And this is the seasonal component. And this is, of course, noise. Okay, that here. Now, as an alternative, which is useful, for example, when you have like seasonality that have just few like outlying months, but the other ones are very close to each other. Maybe sine and cosine, we saw that actually we could probably throw away 3 cosine and sine variables here. So that the cosine number 5 and cosine 6 have non-significant coefficients. So we could throw them away. And I think it was also sine number 3 that has a non-significant coefficient. So we actually could model in a decent way the seasonality, maybe just using 4 cosine and 4 sines. Alternatively, he suggested we could use dummy variables or one-hot encoding of the month. And we can do that in the same way. We keep y, t, okay. We keep the same trend. Well, my plus looks like the t. So. And then instead of using sine and cosine function, we have like, I don't know, A1 times the first dummy variable, the one of January, then A2 times the dummy of February, and so on. Actually, one would say, okay, I will come up to the 12th dummy, and then there is the noise. Okay. But here we have a problem. Does anybody see a problem here? So how are the variables, dummy variables made? Well, this is probably 1, 0, 0, 0, and then goes, and then, so this is January, February, and so on. This is again January. So this is going to be 0 and then 1, and then 0, 0, 0. Is that clear how the dummy variables are? Okay. It's just the one hot encoding of the name of the month. Okay. So, well, sorry, this is 12. Should be this way. So what's the constant? Well, the intercept is just beta 0 that multiplies a constant of 1, usually. So does anybody see a problem with this regression? It's redundant, right? Because you can obtain the constant by just multiplying, so the constant variable, so the one that doesn't appear, but actually you can think this as B0 multiplying a 1. So this regressor here, you can obtain just by summing these regressors. Indeed, this is, it's called perfect collinearity of the regressors here. What does it mean? That you have to throw away one of either the intercept or one of the dummy variables. We need to change slightly the interpretation. If we throw away the intercept, then this becomes the intercept of each month. Okay, if this is no more there, we keep all the 12 dummies, and it means that A1 becomes the intercept on January, A2 becomes the intercept on February, and so on. So it's like the same straight line, but it moves up and down according to the intercept of that month. So they're all parallel lines, right? And the intercept is governed by the coefficient of the dummy variable. If we, for example, throw away the dummy of December and keep the intercept, what's the interpretation? Well, in December, all the dummies are 0. This is already canceled. So all the other ones are 0. And so beta 0 is the intercept of December, so of the missing dummy. What about when it comes to January? When it comes to January, this comes to 1. So the intercept of January becomes beta 0 plus A1. So A1, A2, A3, and so on are just the increment of the intercept of that month with respect to the intercept of December, of the missing variable, okay? So you can do both. But this doesn't eliminate the problem that I showed you before. So the fact that actually, if I take, okay, I throw away one of these. If I take this part here, I have a distorted seasonal component because they don't sum up to 0. Okay, they don't have to sum up to 0. And we say over 1 month, or sorry, over 1 year, all the seasonal component that has to sum up to 0. Okay. And if we sum all these alphas here 1 is missing, then we don't get 0 usually. Okay. How can we solve this problem? This is not so immediate, but there is a way to correct the dummy variables so that they deal with the problem. One simple way is let's design the variables but in a slightly different way. Instead of putting the zeros here, let's put numbers, equal numbers, that makes the sum of this be equal to 0. So if we put 1 here and then we put minus 1 over 11 for all the other one, then it will sum up always to 0, and we will get the property that we're missing. So we slightly modify the way we define the one-hot encoding so that the components actually always sum up to 0. And so we can call them the, I don't know, the corrected dummies or the unbiased dummies. So we'll redefine them. For example, in general, so the first one would be just 1 in the period number 1. Then we have other period. Well, this is monthly, so 12 periods. And we put minus 1 over S minus 1. Here S is 12, so indeed, if I compute the sum of this, it doesn't matter if I multiply by a constant, in our case, S is 12, I would have 1 plus 11 times minus 1 over 11, okay? Which is equal to 0. So this is a trick you can apply to get the dummy variables to act as if they were really building a proper seasonal component. But that's I mean, for prediction, it doesn't change. If your aim is only predicting future value of the y, you don't have to correct the dummy variables in such a way. If you want to instead look at the trend component and the seasonal component as if they were separate things, then you should do this, okay? If you want just to predict it, the prediction really doesn't change. We're just representing the same information in different ways. We're not adding information there. Is that right?
Yes. Well, if you want to do this easier, this would be unbiased.
Of the seasonal.
Actually, some reason behind everything. When I start with some zero, is that also what some?
No, as I told you, the seasonality in some way has to disappear over 1 year because the seasonality is there because we have sub-year data. Take the example of the GDP. The GDP statistics we have at quarterly level, but we usually are more interested at yearly level, annual level, okay? And of course, if you produce statistics of the GDP at quarterly level, they have to sum up the yearly level. So in the yearly level, there is no seasonality. So the seasonal component have to sum up to 0. Otherwise, you would have a biased estimation also of the annual GDP. So that's the reasoning behind this. Of course, here we have a slight problem. We are working on the log of the data. So even though this is summing to 0, we will still have some kind of bias, a small one, if we sum up over the original data. Because of course, here it will sum to 0 on the log, but when I take the exponential, then the effect of the seasonality would have a slight effect, unless I correct it. But it's so small that usually you can just. But if we work on usually the GDP, for some reasons, you can also model on real data, not on log. And because in that case, it has to be so. The seasonal component has to disappear if you sum up the monthly GDP effect. Because otherwise, you would have a different level of the GDP due to seasonality over 1 year, and that doesn't have any reason. I don't know if I kind of.
Yes. Which modeling, right? Modeling,
well, by definition, we know that an annual GDP is the sum of every quarter in the year, and of course the seasonal component doesn't have to modify the sum of the GDP. You sum over 4 different periods, and you have to get 0. That's basically okay. We can just quickly try to build. We can build also the standard seasonal dummies. I'm sure there are many packages that do that, but I never remember the names of any of them. So we can write our own code to produce the dummy variables. Let's see, any clue? So we could, I don't know, we could just start with the matrix of zeros of 144 observation and 11 months. As I told you, we just need 11 months. We don't need 12. And then we can just, I don't know. Any clue what's the best, the quick? Every time I solve the same problem, every time I have to reason about that. I don't remember the best solution. Of course, we can use like a 4-cycle and integral division for examples, or yeah, integral division is the only thing that comes into my mind. You know, you have, or we can just, well, in this case, this could be also a solution, a very quick and dirty solution. Yeah. So this is not a very elegant solution, but it's very quick. Okay, not a very elegant solution, but but it was very simple to implement it. Of course, with integral division, it's much more elegant, but it works. Look at this. So this is the dummy of January, the dummy of February, and so on. Is that clear how I created that? So the Diag12 is just producing an identity matrix of 12 by 12. And then I'm just stacking 12 then because we have 12 years. Okay. And of course I have 12 months, and now I can throw away some months. So if I want to throw away the last month, I just throw away, I just write column minus 12, and it would be solved. Is that clear? It's a dirty solution. If I had to write a function to produce the one-hot encoding, I wouldn't use that. Actually, the formula of R does one-hot encoding if you pass, for example, the months, the name of the months, a variable with the name of the months. Then the formula is going to make this one-hot encoding in an automatic way. But anyway, this is a quick solution. Okay, I didn't put the minus 1/11th. We could do that. We just have to substitute the zeros by minus 1/11. We can try to do that. Again, quick and dirty. Okay, that was it. And of course, now if I compute the mean of the columns, I get, well, virtually 0. Okay. Is that clear? As I told you, not a very elegant solution, but it was quick to think of. So we can kind of do the third regression. And in this case, we can just, again, maybe I can build a W matrix by C binding the counter and the DD matrix, again, D matrix. And I can eliminate December. Yeah, I could have used also some naming here. Maybe we can give some column names to DD. Maybe we can call from D1 to D11. Well, here D12 actually. Okay, and that's it. Of course, then I will put on the e-learning all the code I'm writing here. Okay, as you see, actually, the intercept is exactly identical as the other one because we finally built also a dummy-variable based seasonality that sum up to 0. And so these two numbers are just the same numbers as we saw before. Because we're actually, again, we're just representing the same information in a different way. So there is no practical difference as far as prediction are related between these two models. But for example, what we notice here that actually the first dummy, the second dummy, they're not, again, if we pretend these are reliable p-values, we could throw away these dummies because it looks like December, well, December is the one that we left out. So January and February they have this very similar behavior as December, and also October as well. Also October seems to be very close to 0. So again, we could throw here away probably 3 variables and represent a decent version of the seasonality. Okay. But if we leave all of the sine and cosine function and all the dummy function inside the model, both models will predict exactly in the same way. Okay. Indeed, if you check also the R square of the model, there will be just the same. So 0.9824. Here's the same. Okay, we're predicting exactly in the same way, just using different instruments. Again, here we could also build, as we did before, the trend component, which will be identical to the other one, and the seasonal component, which again will be identical to the other one because we didn't throw away any information. But the prediction will be just the same for both models, and we carry out the two predictions, and then we can stop here. Maybe we can build the first prediction using the predict function. We use the Reg2 model, and we have to provide the regressors, which in the first case are x from 121 to 144. Didn't like it. Sorry, the rows, not the columns. I'm just flipping out. Is that this way? I have to check. So new data. Actually, it should be the same. It wants a data frame. Yeah, there's 24 rows, but why was 100? Well, sorry about that. I always have to fight with the predict function. They work differently in every different model. The Reg2 was actually correct. Let's make it like this. Let's make it this way, it's simpler. So let's make a data frame instead of a matrix. And then here we just say regress X on all the variables, and we pass the data. Okay, this is just the same thing written in a different way. And we do the same thing here. The point there, the dot, means regress on every other variables. And hopefully now it's going to work. It doesn't. Okay. Okay. Actually, the two predictions should be just the same. Or right here. Okay, you see, which we use two different ways to represent the seasonal component, but that doesn't change anything as far as prediction is concerned. We're just representing, as I told you, the same information in two alternative ways. But the two alternative ways may be useful in different situations. Now we're like using all the information. But for example, when we're predicting using hourly data or daily data, we cannot afford to keep all those dummy variables or all those sine and cosine, okay? We have to pick the important ones, okay? And if the seasonality changes smoothly, then we have to go on the trigonometric representation of the seasonality, because with just few variables, we can represent very smooth functions, periodic functions, which are smooth in time. On the other ways, for example, if we see a sudden jump in the data, for example, in Italy in August, then that jump is probably fit better by a dummy variable rather than a cosine or sine, because you need many cosine and sine functions to represent a drop, a sudden drop, okay? So according to the high frequency data that we have and how they behave, we may want to use a mixture of the two ways to represent the seasonality, okay? So that's one point. And then we stop here, but I mentioned this is, there are also other ways to represent seasonalities. I don't know if you ever been exposed to splines, you know, spline functions. For example, you can turn the spline function to become periodic splines and use them also for fitting, well, actually mixture or smooth and not smooth seasonal components. Because spline function, they are smooth, but there are ways to make them not smooth. So these are the most used version of the seasonal variable you can use, but you know, splines, periodic splines are also another solution. Okay, we stop here and try to maybe put some words between the lines of the code so it's more readable, and put it on the e-learning website before Monday. Any question? Oh no, Carol. Kill you.
Would they probably change the interface from?
If you don't use the whole set of either dummy variables or cosine and sine functions, If you will use the whole set, they will provide you exactly the same prediction. As soon as we, for example, cancel some of the dummies or some of the cosine that were not significant, then the prediction will slightly change, because we're not representing that monthly or yearly or 12 points vector. We're approximating that vector, and we are